Welcome back. In this video we are going to talk about word embeddings, and specifically in this video we'll talk about the GloVe model tool, which helps us to generate meaningful word embeddings. Before we specifically discuss word embeddings and what they are, so far we discussed frequency-based models when it comes to the question how we should transform textual information into numerical one. And we also discussed about the the methods that are provided by so-called topic representations. And all of these methods so far, they didn't specifically take into account the context of a sentence and didn't really take a look at the sequential ordering of a sentence and its maybe its meaning that comes along with the ordering and the context in it. So, for instance, if we say after we drive, we drink beer, it's obviously quite different than saying after we drink beer, we drive, because that may, occur in very, very different outcomes. And so context can be important. And the question is now, how can we quantify context when we're transforming textual information into numerical information? And one possibility here is to generate so-called word embeddings, which just means that for each word we will generate a series of numbers that is collected in a vector. So we have a vector representation of a word, and hereby we want to use methods that allow for to include similarities in terms of the meaning and of the context of the words. So that means words that are meaningful in a similar way should have very similar numerical representations, meaning they should have very similar vectors. And this is what is a word embedding or a word vector, and what's the aim of it, okay? I mean, obviously the first time when you hear about a word vector, you have no clue what that is. So let's just take quickly at a small example with some meaning. I mean, later when we have a word embeddings, the actual numbers, they will not have a meaning that is directly interpretable, but for the moment assume we're taking a look at animals and measure them by take a look at the attributes of animals in terms of their size and how dangerous they potentially are to us as human beings. Okay, so, and I mean, this is totally made up in my mind, so do not really know if that's true or not, and there are really exact numbers here, because obviously I do not know how we could really seriously quantify how dangerous an animal is. Okay, but maybe you could treat this as a silly example, and I hope you get the idea. Okay, so if we have a two-dimensional representation, that simply just means we always use two numbers to identify an animal here, and we do not identify the animal, we mean we identify the word that represents the animal. Okay, so we have a mouse, we have a dog, we have a cat, we have a snake, and we have a shark. And obviously, for instance, the mouse is the smallest and is not really dangerous, so that's that point here. And then maybe we have like a cat, which is larger than a mouse, but typically on average, it's larger than a mouse, and also maybe a little bit more dangerous. Okay, then we have a dog, and I mean that doesn't really make sense here, because I would guess on average a dog may be a little bit taller, but let's say, okay, we also are taking into account very small dogs, and so on average they maybe are a little smaller than a cat, and sometimes they may be considered to be a little bit more dangerous because they can bite you and can really that can be quite harmful. Obviously, sometimes more like the bigger dogs are dangerous. But then we have the snake and the shark. And obviously the snake and the shark may be more dangerous to us, depending on the species. And obviously if a shark thinks if we are something that it can eat, otherwise obviously it will not attack us. But anyway, we can see that by using two numbers to describe the word of the animal, we have here a two-dimensional representation, which shows us where each animal lies in a two-dimensional vector space. And so that is how you can picture what is meant that a word is represented by a vector. Okay, so that just means we have a word and we have certain numbers that represents the word. And the similarity of a vector, that we'll come to that in a minute, obviously, means that as already explained in the past videos, when we have vectors, we can quantify the similarity between vectors by using concepts such as the Euclidean distance or, for instance, cosine similarity. And here, for instance, if we take a look at the Euclidean distance, then we will find out that the dog and the mouse, they are more similar to each other than the dog and the shark. And I guess that's true also in reality. Okay, and so that's how you may picture it. Okay, so what stands behind the idea of transforming words into vectors. And later we will not really take a look at those numbers. So the exact value of those numbers is something we do not really care about. The only thing we care about is that we can see similar numbers here if we have words that that share a similar meaning. Okay, or if words are similar meaning means also they're used in the same context more or less. So in real life, or like when we really do this, and the typical word representations, they are not really only 2 or 3 dimensional, they are rather high dimensional. So like 50, 200, 50, 100, 200, 300 numbers are typically used to represent a single word, okay? Because language is very complex and we need rather high dimensions to really grasp the idea of language and its context, meaning, and so on. And obviously also the numbers is something, so what numbers should we use for a certain word? That is something that's going to be estimated by a model. So you can treat each vector for each word is defined by a certain certain amount of numbers, and each you can treat them in your head as parameters of a model. Okay, so meaning we are going to estimate all the numbers that are going to be used for a word embedding. So like if you would have used 2-dimensional embeddings, that means those numbers here are all unknown to us and we're going to estimate them. And when we want to estimate them, obviously we need a model and we need to aim for that model such that the parameters can be calibrated in order to succeed in the best way that is possible for achieving the aim of our model. Usually that's reducing a loss function. So that's like the introduction, how you may picture what is meant by a word embedding. Word embedding is just a synonym for word vector. Okay, so we embed the meaning of the word in a vector. That's why it's called word embedding. And there are different approaches how this can be done. And I would say popular ones are the word-to-vec model, which has been before the Glovey model, and also the Glovey model. But personally, I think the Glovey model is a little bit more easy to understand, and that's why we're starting with that one here, okay? We go quickly through the slides here, and then we take a look at a small example, which I think makes it rather easy to understand the basic idea of the Glovey model and how it is generating word vectors. Because I think once you understood the concept of once you get the idea, or once you can picture what is meant by representing a word with a vector, then there are only like two or three things in general that needs to be understood when we talk about the Glovey model. Okay, the first thing that needs to be understood is the Glovey model stands for like a global representation, and global is here because we're taking a look. Typically, we have a corpus, and which is the set of documents, and the global vectors are called global because the Glovey model is built on a word-word co-occurrence matrix that is based on the whole corpus. Okay, so that means first thing you need to understand is what is a word-word co-occurrence matrix. And so if you have a certain sentence, so I like text analysis, then we take a word in that sentence, for instance, text, and then we take a look which words do occur in like in the context of this word. Okay, so if you have I like text analysis, and if you use a so-called window size of 1, meaning just we take a look at the one word to the left and one word to the right of that word. So I like text analysis, meaning text is on the left we have like on the right we have analysis. So that means like occurs for one time in the context of text and analysis occurs for one time in the context of text. But for the Glovey model, we calculate the numbers how many times in all documents the certain words occur in the context, for instance, of the word text. Okay, and that's like the word-word co-occurrence matrix that occurs, meaning if we have D words in our overall corpus, so D terms, unique words in our corpus, for each word we take the word, right, text, then we scan all the documents and always take a look, for instance, how many times is the word like in the context of text. So in our overall document, maybe like is standing for like 12 times on the left to text, then we will collect text like 12 times, or like on the left, maybe like for 12 times, either like stands to the left or to the right of the word text, then the co-occurrence of the word text and like will be 12. Okay, and this is like the co-occurrence matrix. We come to that in a later point. So that meaning is global because we globally scan all the documents, the overall corpus, and check out how many times does a specific word occur in the context of another word. Okay, and that is represented here by that notation. So so if Cij is, for instance, 5, that means the word J occurs for 5 times in the context of word I. Okay, and so let Ci then be the number of times any word appears in the context of the word I. Then we can take a look at the relative frequency in order to estimate the probability for a certain word co-occurrence. That means, for instance, let's say so if the word, I don't know, like occurs 12 times in the context of text, but overall the word like occurs 100 times in the overall corpus, then in 12 out of 100 times, so with 12% probability, the word like is going to be used in the context of text. Okay, so those are like the word probabilities that we can have here. And that needs to be understood. Okay, like what is a co-occurrence of words and how do we count them? That's like the first thing we are going to do. So if we have, for instance, a sentence like here, if beer is too warm, it tastes not really good, then the window size is something we need to set. So let's set the window size instead of 1 to 2. Then we take a look to the left and to the right for 2 words. So if then for like tastes is here in the middle, then we go to the left and we have warm and it, and tastes to the right is not really. So that is like the context of the word tastes, and now we can collect, we can count, we can do this for the whole corpus, and we can count, for instance, for how many times does the word warm occur in the context of the word taste or tastes. Okay, and then the next step that I think makes the GloVy model so powerful and also so intuitive, and I think this is a very creative and nice approach that has been found here, is that we do not really directly take a look at the probability itself. We are not really interested if like is very likely to occur if we're talking about texts. We rather take a look at the relationship between probabilities. And I think this is like from the original paper, and I think this example really makes it quite clear why this is so useful. Okay, so here, for instance, we have we take a look at the relative frequency of the word solid in the context of ice, and also, or like I think it's rather the other one, like. This is the probability of the word ice in the context of solid, and this is the probability of the word steam in the context of solid. So this is like from a true example and like from a big, large corpus with a lot of text in it. So we can see like those are the absolute or the relative frequencies. How many times does the word ice occur in the context of solid in relation to the number of times the word solid is used in that corpus. Okay, so that's like the numbers are here quite small because obviously you know there are a lot of other words that are used in the context of solid, not only ice or steam. But now if we take a look at the ratio here, so the ratio of how many times, or what's the probability for using ice in the context of solid, and what's the probability for using steam in the context of solid, we can see that this is a rather high value. And this brings meaning to it, because ice and solid is something which obviously matches better than steam and solid, because per definition steam isn't something that isn't really solid at all, okay? And so then we have a large value because we have ice here above. And now take a look at gas. Obviously gas seems to be way more related to steam, and that's why we have a very small value here. I mean, if we would take the reciprocal here, that would be like the other way around. So meaning if we have a word, or if we compare two words and we have a third word, then the relationship for the probabilities of those two words is drawn into that direction, which makes more sense in reference to the third word. The third word is here called the proby word, okay? And then there may be words that are rather similar, have a similar meaning. So for instance here, for ice and for steam, water is obviously something that is similar and comparably important, because obviously water is the basis of ice and steam. So we have a value around 1 here. And also if a word is completely unrelated to the two things, like fashion, also the ratio is approximately at 1 here, okay? And I mean, just take a look for yourself at the example and think about it for a moment, and then hopefully it will work for you as it worked for me. And I think this is really a very creative and nice way to work out relationship among words and their meanings, okay? And this is like, I would say, one of the most important building blocks when understanding the Glowey model, okay? First of all, you need to know that we're talking about word co-occurrences globally over all documents. And now the idea here is to work out similarity of words by their meaning in relation to each other. Okay, so this is like, I would say, the backbone when it comes to understanding why the model works so good. Okay, and now let's go to the technical development of the model, and I think we can go quite quickly through that, and it's maybe best also to take a look at the original publication. So if you just Google for Glowey paper, you will find that. And so we are here, right? And so on the basis of the observations that are made here, the idea is now that we will have word vectors, right? Which aim to rebuild the relationship of the probabilities. Because if we succeed in doing this here, then the relation and the relationship among words, that obviously seems to be very good catched in a good way by taking a look at the ratios of the probabilities. If we can work that out by using vector representations of the words, then obviously the vector representations should resemble, or should also be an equivalent to the illustration or to the quantification of the relationship of the probabilities here. And we will not go in detail through that, but if you are interested if you have time, as you can see, it's only a few lines here and only a few sentences, and here we actually end the model. But this is really also what I think makes it so nice, because the way from here to the final formulation of the model is marked by using, I would say, not simple but basic and fundamental knowledge of linear algebra, and this is what I really like about, to be honest. Okay, but in the end, what we will have, a prediction kind of problem, and solving this problem will leave us with good vector representations that catch the meaning that is also catched by those probability ratios here. And as you can see here above with this example, that this really is able to catch the meaning. Okay, so what we are doing in practice now, or if you want to build the Glowey model, is that starting from the formulation here. So here we have like the proby word vector, and we have like the two words that we would like to compare. So in our example, like the proby word vector would be the vector for instance, for solid, and then we have the two word vectors for ice and for steam, and that's where we start. But like solving or finding these vector representations can be done by solving this here, and that means there's a slightly different notation in comparison to my slide, so sorry about that. X, Y, K is what I'm referring to as C, Y, K or C, Y, J in the slides. But basically what's done here is that we calculate the dot product of the vectors that represent the word of interest and the context word, so the Proby word. Then we also have just some bias terms that we can ignore for the moment. And we're trying to by generating the dot product of the vector representations, we're trying to estimate the co-occurrence of those two words. Okay, so it's like a supervised regression type problem. And then there are some fine refinements in the model that take care of problems such as how are we going to proceed with co-occurrences that do never occur, and how are we going to work with co-occurrences that really occur a lot, so that potentially could dominate everything. Those are like some I would say not say minor, but this is treated here. But for the moment, for you, you should just understand like two things. First of all, how the meaning is built. The meaning is built by the relations of the probabilities. And then we're trying to catch this idea and solve this and transform the information is given here into word vectors. And this is done by building a regression type problem. Okay. And now we're going to back to the slides, but also in a second we're going to my notes on the iPad, because here I want to explain this to you with a small example, and I think then it will be really clear, and you will find that this is rather similar, or rather not similar, it's rather easy, I would say, comparably to understand, and more easy than it may look like at first sight here. Okay, so here we are with a small example. So think about that we have two documents given by those two sentences here. So I love text analysis and text analysis is great. Okay, so if you would like to generate word vectors out of this corpus here, according to the Glovey approach, then technically what we need to do first is to build the co-occurrence matrix. And here, for instance, let's assume we're using here a so-called window size which is equal to 1, and we are looking to the left and to the right. Okay, so what we do is, for instance, for analysis, we take a look at analysis. We have this here and here, and then we take a look at to the left and to the right, and to the left and to the right. Okay, and we can see here that if we have analysis as a word, then in the context of analysis, the word text is occurring for 2 times. That's why we have a number of 2 here, and we can see that is occurring for a single time. Okay, that's why we have a value of 1 here. Okay, so do this one more time for another example. For instance, if we go to grade, we have a word grade only occurring here for 1 time, and then we take a look to the left and to the right with a window size of 1, meaning just to the word to the left and to the right of it. And obviously only is occurring for 1 time in the context of grade, and no other words are occurring in the context of grade in our corpus. And I hope you get the idea. So that's how we are generating in the first step the word co-occurrence matrix. Okay, and now technically what we're going to do is we are going to go through the word occurrences or co-occurrences, and like not the 0 ones, but to the ones where we really have co-occurrences, and try to make a prediction problem out of it using word vectors. Okay, so initially we will start with word vectors. Each of the word vectors has now a dimension of p. So if we have overall, for instance, d words into our corpus, so 1, 2, 3, 4, 5, 6, So here would be D is equal to 6. So for instance, P usually obviously is a smaller number. Let's assume in our example that would be, for instance, 3. And in reality, it may be, as I said, 100 or 200 or something like this. Then we would have the matrix with word vectors. And those vectors are representing the words in the middle. So we would have for analysis, for instance, a vector which is called U, and we will have, it would look something like this, okay? So I make just the A for analysis, sorry, to make it shorter here. So, and those are like 3 numbers that would be in the beginning randomly initialized. So meaning in the beginning we just start with some numbers here. And then we also would use a second matrix which has word vectors for the same words, but those are now the word vectors that occur or that would be used as the context word vectors. Okay, so that means, for instance, in our example here, one of the first co-occurrences we may take a look at is this one. So analysis and is. So that means we also would take a look at the vector of V for the word is, and that would also be a 3-dimensional vector. So it would look like this, and again, those are just some numbers that are randomly initialized. And then what we do here is we calculate the dot product. Okay, so that means so I think you can work this out on your own, but let's just do it. So that would be this times this plus and so on. And then also what is done in the model, which further improves the ability of the model and the flexibility, is to add some bias terms. But I mean, calculating the dot product here is a scalar value. So what we do here, we use this dot product, which is just in the end a number. Then we add other parameters to the model, which just makes it more flexible. So the bias term referring to analysis plus a bias term that is referring to is. And that's supposed to be now the log of the co-occurrence. So here the log of 1, because we have here a value of 1. Okay. And now to make a really prediction problem out of that, we use the squared deviation. So the loss for that couple here, so the couple analysis and is, would be the log of 1 minus the dot product of analysis and the word vector is minus the bias terms. Okay, and obviously we are not only going to do this for this single co-occurrence couple of analysis and is. In our small example, we would iterate through all the non-zero co-occurrences in the matrix and would proceed in the same way. And then after calculating the loss, very similar as for neural network models or any statistical model, we would, for instance, use the gradient descent algorithm to improve the parameter values, meaning the word vector representations as well as the bias terms, in order to reduce the loss, such that the word vector representations finally, once we succeeded in estimating the model, are a good and close representations of word co-occurrences, right? And this is basically what the model is about and how it works and how it manages to really generate meaningful word vector representations that especially are built on the relationship between words by the relation of their probability regarding their context frequencies. So I think from a technical perspective, at least the basic idea, as I try to to write it out here. I think it's rather simple once you understand what a vector is and how to work with a vector. And basically, you're just trying to make word vectors that are suited to predict the co-occurrence of those two words. So that's like the idea of the model, or that's like what's technically happening here. And then there are some, I would say, like fine refinements that needs to be done to really efficiently estimate the model. How do we handle words that, or word pairs or word co-occurrences that rarely randomly occur or that occur very often. Then in the original paper you will find some information how this is done with a weighting when we calculate the loss, and the weighting is given smaller weights to low co-occurrences, and also it, as you can see here, but if the occurrences are rather large, then it's kept the weightings such that we do not have a model that is completely dominated by very frequent word co-occurrences. And furthermore, as you have seen, we have two word matrices, and in each matrix we have a row that represents the same word. So what's done in the end, after the both matrices are estimated, the original paper, I don't know if I really find it in a second, but it sums both vectors in order to build the final word vector representation of, here we have it. So within this in mind, we choose to sum those two vectors as our word vectors. So meaning the word vector and the context vector, u and v of the same word, they are summed up in order to generate the word vector for the specific word. Okay, and this is more like technical details. And I could really recommend you to read the paper. It's not that long, and I think it's quite brilliant, and especially the idea also, I think in my opinion, is quite brilliant, and a very good model to generate word vectors. And if you Google here, so if you Google just for Glovey paper, then also you will reach or you will find the Glovey Stanford homepage by the developers of the model, and there you will find a more interesting information here. And there are like 2 or 3 things that we can do. We can either estimate if we have a corpus, we can either estimate the Glovey model by ourselves, or we can use then word vector representations of words that are already pre-trained. So here you will find pre-trained word vectors. You can see here what was the basis for estimating those word vectors. And I think somewhere here we find also the dimensionality, like those. Okay, so you find vectors of different dimensionality in the pre-trained vector set. But like handling this and how we do this in practice and how we can really use those word vector representations is something that we're going to discuss in our Zoom sessions. So this video was just to show you the initial idea of the Glovey word vector representations. In the next video, we're going to discuss the word-to-vec model, which is, I would say not really. It's obviously it's similar because it generates word vectors, but its initial idea is quite different. Nevertheless, at least as I think even more popular than the Glovey word vector model, and by that way, that is meaning also very interesting. So be excited and take a look at the next video, and see you there. Bye bye.